I'm Raya. I'll be chairing this session on neural architectures. And our first speaker is Patrick Schwab. He's going to talk to us about the paper Not to Cry Wolf, Distantly Supervised Multitask Learning in Critical Care. Please welcome Patrick.
Thank you for the introduction. So this is a paper we've done in the intensive care unit, so it wouldn't have been possible with without our clinical partners. So this was in close collaboration with the University Hospital of Zurich. A big shout out to them. And since I couldn't bring you to the intensive care unit, I brought a little bit of the intensive care unit here. So it's a short, sorry. Yeah. No, I'll restart it. No. Doesn't want to work. No. Well, this pink block, oh, no, it works. So basically, this is the intensive care unit. For those of you who have never been in this environment, as you can see, people here are both supervised by clinical staff as well as many, many monitors. You can see plenty of them in the screen right now. And this is just one side of the bed. If we move to the other side of the bed, we see even more of them. And a great issue in this area is that these monitors, they all produce alarms, and a whole lot of them. On average, in our ICU, around 700 per patient per day, and we have 10 patients in there every day, so that's many thousands of alarms that we get. And previous studies have shown that 70 to 90% of these alarms are actually false. They require no intervention at all from the clinical staff. So what happens is that people get desensitized, they ignore these alarms, and once in a blue moon there comes an alarm that is actually important and it's missed. And there's been studies on this as well. There's a few hundred deaths associated with this in the United States alone. So naturally, as a machine learning researcher, I thought, what can we do for these people? How can we make their environment better using machine learning? And the idea is actually quite simple. So we're using these monitoring systems, and we are getting at time point t equals 0. This is indicated by this dashed line here, an alarm. And what we do is we check the prior history of the signals up to a specific length, and we check whether there was anything that indicates an artifact or a technical error. And these alarms we can route either to be suppressed or reported with a lower urgency. And if we think it's a proper alarm, then we route it to the clinical staff or the nurses to be actually seen. And this is what we call smarter monitoring. And the basic challenge here is actually we have a lot of data. We have all these monitors that are collecting 100 to 200 hertz 24/7, up to 20 monitoring systems at the same time. But we do not have access in the same amount to labels. And labels in this area are really hard to come by because we need multiple clinical people, clinical experts to label these data sets for us. And it's very expensive and very time consuming. So a big challenge here is, can we make do with fewer labels? And this naturally leads us to semi-supervised learning. And just a quick recap, so there's currently 3 main areas to semi-supervised learning in deep learning. And the first one, and this is the one that we're concerned with at this talk, is distant supervision. It's also called in different disciplines self or sometimes weak supervision, but it's all the same concept. One approach in this area from the recent history was temporal ensembling. Secondly, there's broadly approaches based on reconstruction. So they basically use, along with the main task, another secondary objective that is based on a reconstruction task. And this could be autoencoders, variational autoencoders, and ladder networks. And thirdly, we have adversarial nets, which is quite popular recently. And in this category, we have things like feature matching GANs, CAT GANs, triple GANs, and a whole lot more. And I will be going in depth a little bit more in the first two, because there's a few analogies there that actually motivate our approach pretty well. So if we look in detail at reconstruction-based semi-supervised learning, it's actually just a special case of distant supervision where the auxiliary task is a reconstruction task. And this naturally leads us to the question, why this task, why not another task? So reconstruction is actually a really convenient auxiliary task because any model, any task, any kind of data can be reconstructed. But is it the best one? And we reasoned that, no, actually, there could be better ones, and we have a few empirical data points on that that show this could be true. And we reasoned that basically two hypotheses. Firstly, we reasoned that more related auxiliary tasks might be better than just reconstruction. And also, we think that having multiple diverse auxiliary tasks at the same time might be even better than just having one. And to test this, we basically had to design a new architecture that can integrate basically effectively a large number of auxiliary tasks for distance supervision. We started out with something that could model this problem domain. So what we have here, we have multiple, this is really the main part, we have multiple input streams, and each of them is modeled what we call by perception block. And these are basically just neural networks with their own parameters, etc., who are specialized in recognizing patterns in this form of data. Each of these perception blocks is accompanied by a missing indicator, which is basically just there to handle the missingness that is very, very common in this kind of data. Next, we basically expanded on this approach, and we added something actually very simple, a simple thing that we call a multitask block, which is simply placed on top of these perception blocks. And their main purpose actually is to host these little black dots here. These are the auxiliary tasks that we will be using to do distance supervision with multiple auxiliary tasks. In this setting, in this illustration, I'm showing 3 auxiliary tasks, but actually this architecture scales to an arbitrary amount of auxiliary tasks. In our experience, we do up to 100 auxiliary tasks in the same neural network end-to-end trained. And all of this information from these multitask blocks is orchestrated by the head block in blue here, which is trained only on the main task. But all the information flows down to the perception blocks, of course. So this is a cool architecture, cool toy, but actually we need 2 more things to be able to test these hypotheses. So actually, where do we get these auxiliary tasks from? Because we need a large set of relevant auxiliary tasks to test this. And also, secondly, when we train with a lot of auxiliary tasks at the same time, end-to-end, there is bound to be some conflicts in the tasks happening during the training. So how do we deal with this? So for the first issue, actually we take quite a repository-based approach. So we take a large multivariate feature repository for time series. So things like autocorrelation at different lag levels, power spectral densities, etc. And this is a really large feature set, more than 2,000 features. And we try to identify those features in this set that are relevant to the main task. And relevant in this case, we're defining as significantly correlated with the labels. And out of this subset, so we have now a subset of relevant tasks out of this whole pool of tasks. And we're interested here, how do we pick out of this subset now the tasks that we use for distance supervision? And in the paper, we're actually using 2 very, very simple strategies. And we're proposing at first random selection out of this set, so just picking at random. And secondly, ordering them by their importance in relation to the main task and picking them from the top down until we have enough tasks for our architecture. And we evaluate both of these approaches in our experiments later on. And secondly, we're commenting also adverse gradient interaction. So this can be a problem if we're training on many, many, many different tasks at the same time. And basically what we do is we disentangle the training of the unsupervised auxiliary tasks and the supervised auxiliary tasks in an alternating fashion. You can imagine this is quite similar to the approach in GANs, where you're basically alternating between discriminators and generators. But in this case, it's not an adversarial game, it's actually a cooperative game. Both these tasks have the same goal, they just use different objectives. And then we performed a large-scale evaluation on this. Around 3,000 models were trained here. And just to explain this whole graph thing that I'm going to do now, first of all, at the top, you see the metric we're using. The metric is the ARC at a specific point at a level of labels. So in this case, it would be 12 training labels that we used evaluated on the test set. And at the bottom, you see all the different models we tested. I've color-coded them for you in roughly supervised baselines are in green. Then the semi-supervised baselines are in gray to black. There's one representative for each category I told you about. There's distance supervision is the first one. The second one is the ladder network, is a reconstruction-based one. and in black you have the adversarial one with feature matching GANs. In orange, you see different variants of distantly supervised multitask networks with different amounts of auxiliary tasks. So the lowest we tried was 6, and the highest was up to 100. Then we also tried in pink one version that did not use our two-step training approach. It's the pink one here next to the 100, also using 100 auxiliary tasks just to see if it actually helps. And in blue, there's the ones that are using the distantly supervised multitask networks that are using random selection as opposed to importance selection. And the rightmost one is a bit of a special one. It's using the one with the D. It's using the auxiliary tasks not distributed in width, like in our architecture, but distributed in depth sequentially to see if width is actually better than depth. So our first result was basically we evaluated distantly supervised multitask network at 25, at 50, and at 100 training labels used, and we see that it outperforms quite comfortably all of the Semisupervised learning algorithms in gray to black here. The black line is the top performing model here. An interesting point to note is that we see in the orange ones that are trained with the selection by importance, that actually it's not, the network is not able at this low level of labels to make use of all these, effectively make use of all these added tasks. We hypothesize this is the case because we're only training the head block on the labeled samples, which means that orchestrating 100 auxiliary tasks, the information from that with just 25 labels can be quite hard. So this might be the problem here. We see the relationship is actually inverse on the following, on the higher label levels. Next, we also tried to find out which of these selection methods is the best. And as I told you, I evaluated random and importance-based selection. Importance-based is in orange here, and random selection is in blue. And we're comparing here the one with 6, both of them are using 6 auxiliary tasks. And we see quite clearly that at these 3 label levels, the one by random selection is actually outperforming the one by importance selection. We reason that this is because diversity might be an issue here. If you're selecting by importance, there is a big chance if you have a large number of features, then there's a large chance that you have more similar features at the top, because similar features obviously perform similarly as well. And by random selecting, you actually avoid this issue completely. Next, we also found that our prevention strategy for adverse gradient interactions was effective. Here again, in the deep pink is the approach without our strategy. And in gray is the naive approach, where we're just appending the auxiliary tasks to the head block. And we can see that both, so the one with our strategy is the biggest one here in all 3. And we see that it's compared to both, it's actually better, and actually without it, it fails even to beat the head block-based one. So this is actually a key component. This is what we found. It's a key component in this architecture actually to do this training regime. In conclusion, so we presented an approach to semi-supervised learning that automatically selects a large set of auxiliary features from multivariate time series. It scales to hundreds of auxiliary tasks in a single network trained end-to-end. It combats adverse gradient interactions between tasks. And we also found, so this had been reported in previous works as well, that adverse gradient interactions and auxiliary task diversity might be the key features to multitask learning. And last but not least, we also kind of did good progress on this clinically important task. So there's more details on this in the paper, but we basically, on the highest level, we managed to reduce the expected amount of false alarms by up to 80% with all the labels, and we managed with the distantly supervised multitask network to get close to 80% of this performance with just 100 labels. So it's a very potent approach to this clinical problem. Definitely there's a lot of details that I left out in this talk. It was a little bit superficial, but if you're interested in the details, there's a lot more in the paper and also at the poster session. So please come today, 108 at 1850, and I will be happy to take any and all of your questions.
Great. Thanks. If there's any questions, please go to the 2 microphones there. Yes, go ahead.
Hi, great talk. Thank you. I'm curious, when you said that you were selecting auxiliary tasks, you said you were identifying relevant features.
Yes.
Is that the auxiliary task itself? And then also, when you said the order of importance, how do you actually prioritize these things? Like, what are the labels themselves?
Yes, so the labels themselves come from the clinical staff. So we had 1,800 alarms labeled, so they went really over these situations. They looked at all these data streams, and they said, okay, this is most likely an artifact, or this is most likely a real thing. And we actually did this with multiple, we had a whole committee of medical experts to do this, and we took the majority vote. There was actually a high disagreement, and there's details about this in the paper as well, between the experts on this task. So this is what we're using as the relevance, as the main task. And in order to get the importance, we're actually doing, correlation testing with Kendall's tau, and we're just ranking by the p-value. So it's a simple approach in the importance sense, yeah. And yes, the tasks, so the tasks, what I call tasks, are also features. So this has been shown as well. Good features for a task are also likely to be good auxiliary tasks, so that's why we can do this approach.
Okay, so you're predicting what the features are.
Exactly.
Okay.
And one of the baselines, actually, the one to the left, the green one, is using a random forest on top of these features to compare whether or not using just these features to predict would be better or worse than doing the distantly supervised learning, and actually we find that, yes, it's in most cases better, yes.
Cool, thank you.
Thank you.
So I had one question for you. I understand that the more important problem is to sort of suppress spurious alarms, but did you also, with this data, it seems like you could also try to do advanced prediction of real events by using all of the different, looking across the different sensors that are there.
Yes, that is definitely a next step that we're planning. So basically what we did, we set up this big infrastructure to collect and also store this kind of data. So very few hospitals do actually store this kind of data because it's very high volume, very high resolution, and they don't really know what to do with it. But we set up this infrastructure to save all this data, and we're planning to do in the future as well prediction tasks for different diseases, etc.
In those clinically critical tasks, false negative is also very important. Can you elaborate a little bit on that? Thank you.
So yes, this is actually the big problem here. So a clinician wouldn't accept this approach if it had a very low specificity. That's why also I'm reporting in the paper the sensitivity at 95% specificity. So 5% expected false negative rate. And I think anything higher than that would not be accepted by clinicians. They would not use a system like this with a higher false negative rate. So yes, these systems need to be highly specific, and this is also, this was a goal of us to have a high specificity to make this acceptable. And yes, we reach up to 80% sensitivity at 95% specificity.
Are there specific techniques that can improve that part?
I'm sure there are, but I personally haven't looked at it, but we can talk about it later at the poster session if you like, yes.
All right, great. Let's thank Patrick again.
Thank you.
All right, great. Our next speaker is Bin Dai. He's going to talk about compressing neural networks using a variational informational bottleneck. Let's welcome Bin.
Okay, thanks for the introduction. And now we are going to present our work compressing neural networks using the variational information bottleneck. So it is well known that neural networks are often overparameterized. And the consequences of the overparameterization is that we usually need unnecessary large model size, and the computational cost is also increased, and we need extra runtime memory footprint. So previous works that tries to compress the neural networks include designing more efficient network structure, and tensor or matrix decomposition, and weight quantization. And the first method to compress a neural network is pruning the existing network structure. So we usually have a big network, the original network structure, and then we prune down the original network. So for the pruning methods, there are both works that tries to prune the weight connections, like illustrated in this figure, like this. And there's also works that tries to prune weight groups or activations, like this. So in this method, they try to prune the whole neuron or convolutional filters from these layers. And our work is also a kind of pruning method that tries to prune the neurons or the convolutional filters. So to begin, we first interpret a feedforward network as a Markov chain, like this. And here Y is the target output, and X is the input. And H1 to HL are the hidden layers. So sometimes we also denote X as H0. So it means the first maybe the input layer. And the ith layer actually gives the probability distribution of HI given its previous node HI minus 1. If this probability distribution degenerates to a direct delta function, then this network becomes deterministic. So in our work, we consider non-degenerate distributions. And the last layer of the network tries to approximate PY given HL via some tractable alternative PY hat given HL. So each layer in this network is trying to extract information from its previous layer, while the last layer tries to use the information extracted and to give an accurate prediction. So the more useful information that is propagated through this line and until HL, then the higher predicting accuracy it will be. So however, in a regular neural network, it often extracts irrelevant information in the hidden layers. For example, here we have a Y, the label cat, and we have an input image. This is an image of a cat. And during the network, it extracts a lot of information. For example, the color, the animal type, and the location, and even the mood of the cat, and other informations. And in the last layer, then it will give the label animal type information of the input image. So we can see here there are a lot of redundant information, for example, the color, the location, the mood. So our intuition to compress a network is that in each layer, we want to maximize the mutual information, IHIY, which is the mutual information between the hidden layer and its label information, and simultaneously minimize the mutual information between HI and its previous layer. So it's, this means we only want to extract useful information, but no redundant information like color and locations and mood. So this method is called the information bottleneck, and this is first proposed by Tishby. And here we can see if we add information bottleneck here, it can filter out the irrelevant information. So the layer-wise energy becomes like this. Here, gamma I determines the strength of the bottleneck. But unfortunately, this objective is intractable. So instead of optimizing the objective function, we minimize an upper bound of it. So here, this term is an upper bound of the scaled mutual information between HI and HI minus 1. And this term is an upper bound of the negative mutual information between HI and Y. So here, QHI and QY given HL are two variational distributions. And these two upper bounds holds for any kind of QHI and QY given HL. So our upper bound can be written like this. And since we've derived the upper bound, the next thing we want to do is to parameterize the distributions in this upper bound. So the definition of QY given HL is quite simple. it is a multinomial distribution for classification task, and it gives a cross entropy loss, and it is a Gaussian distribution for regression task, and gives a Euclidean loss. And we define QHI, which is a variational prior of HI, as a Gaussian distribution with zero mean and a learnable covariance. And this prior is learned from the data, and it is often used as a sparse promote prior. For example, if some psi ij becomes 0, then it will push all the corresponding posterior to be a direct delta function spiking at 0, and thus the HI will be sparse. And we define PHI given HI minus 1, which is a direct delta function, a deterministic network, and we define it as a Gaussian distribution like this. So here, the circle dot means the element-wise product, and Fi is a deterministic transformation. In practice, it is usually a concatenation of a fully connected layer or convolution layer, a batch normalization layer, and an activation layer. So this is a deterministic transformation, like in a deterministic network. And mu I and sigma I are two free parameters that has the same dimension of this hidden layer. And to random sample an HI from this distribution, we first sample a Zi from the normal distribution with the mean equal to mu and the variance equal to sigma. And for the gradient to propagate back, we use a reparameterization trick, which means we randomly sample epsilon I from a normal Gaussian distribution and then multiply element-wise, multiply it with sigma I, and then plus it with mu I, and we obtain Zi. And then we element-wise multiply it with the output of the Fi, and then we obtain HI. And because PHI given HI minus 1 and QHI are both Gaussian distributions in our model, so the Carroll divergence has a closed form. So this allows us to optimize the variance of QHI, which is psi I, out of the model. So we can directly calculate the optimal value of psi I and plug it back into this Carroll term, and we obtain this equation. And here, psi ij is defined in this equation, and according to Jensen's inequality, this term is always greater than or equal to 0. So for computational convenience, we remove this psi ij from the final objective function, and we will show such an approximation does not harm the performance both theoretically and empirically later. So the final objective function becomes like this. It is composed of two terms, a regularization term that tries to compress a network, and a data fit term that tries to give a high accuracy prediction. And for later convenience, we define alpha ij as a ratio between mu ij square and sigma ij square. So the final objective function can be also written like this. And the final network structure, we can see the Carroll term is only related to mu I and sigma I, because in this equation, we can see the Carroll term is only related to these things. So the network structures is like this. And this part we already introduced in the previous slides. And here, this should be the Carroll loss term is only related to mu I and sigma I. And all the parameters can be optimized using the variation, using the back propagation. So since we have used multiple upper bounds and approximations to obtain the final objective function, so it is reasonable to question whether our original principles are compromised. So to address this concern, we apply some theoretical analysis on this final objective function rather than our original proposed theory. So first, the regularization term is log 1 plus alpha ij, which is a concave non-decreasing function on 0 to infinite. So loosely speaking, instead of pushing all alpha ij to relative small values, such a regularization term will push some alpha ij to exactly 0, while leaving the others mostly unchanged. But what does alpha ij equal to 0 mean actually mean in our model? And we argue that at any minimum of our final objective function, alpha ij equal to 0 is a necessary condition of that the mutual information between the corresponding neuron and its previous and its previous layer equal to 0. So we can see if the mutual information between a neuron and its previous layer equal to 0, it means that this neuron actually extracts no information from its previous layer, and of course it has no information about the label, so it can be safely removed. So here we can see it has a relationship with alpha ij equal to 0. However, this does not mean that all the neurons with alpha ij equal to 0 is redundant. So to address this issue, we also have that alpha ij is a sufficient condition for the mutual information between this neuron and its previous layer is smaller than psi ij, which we introduced previously. It is always a positive value. And if we further add some other reasonable assumptions, we can also derive that alpha ij equal to 0 is actually a sufficient condition for the mutual information between the corresponding neuron and its previous layer equal to 0. So this means alpha ij can be regarded as an indicator of whether this neuron or this filter is redundant or not. So after training the network, we can prune the network according to the value of the alpha ij. So there's also another kind of redundant neurons. So previously we talked about the redundant neuron, which actually extracts no information from its previous layer. But there's also another kind of redundancy, which means it extracts some information from its previous layer, or even some useful information. But this information is never inherited by its next layer because of the outgoing weight actually equal to 0. So interestingly, we can also prove that alpha ij is actually a necessary condition for this kind of redundancy. So we also theoretically analyzed a tractable upper bound on our proposed loss function. So this is our final objective function, and we use a tractable quadratic upper bound, and we analyze the tractable quadratic upper bound of it. And we can see at any local minimum, the redundant activations will be pruned from the model. So this is one direction that actually is a useful dimension, so there's no pruning. And there are some directions, if the network is over-parameterized, then in some directions, the objective function may be like this, and the bound is a flat thing, and we can prove that such a dimension can be pruned in our model. And the second thing is that unlike previous models, which use like L0 norm or L1 norm to regularize the network, our sparsity penalty can prune the activation that is active relative to the curvature of the data fitting terms. So this helps to avoid the bad local minimum caused by the L0 norm, and also can find the optimal solution, which may be compromised because of the L1 regularization. So for more details, please see our poster, our paper, our poster. And then we empirically evaluate our variational information bottleneck network. So in the training phase, we set the bottleneck parameters such that our accuracies roughly match the accuracy of the existing methods, so we can compare the compression performance directly with them. And after training the network, we prune the neurons in the fully connected layers and the filters of the convolutional layers, which has small alpha ij. Because if we optimize the network using the SGD, it is impossible for the alpha ij to be exactly 0. So we prune the neurons with small alpha ij. And in the test phase, we use the mean value of PHI given HI minus 1 rather than sampling. And we can also use multiple samples that can further improve the accuracy, of course, at the cost of computational time. And we can also fine-tune the pruned model to further boost the accuracy if desired. So we first test our model on the fully connected network on MNIST. So we have we regard the input as a 784-dimensional vector, and there are 2 hidden layers with 300 dimensions and 100 dimensions respectively. And we use 3 metrics. First is RW, which is the ratio between the parameters left and the parameters of the original model, and Rn, which is the ratio between the memory footprint of the pruned model and the memory footprint of the original model. And also we evaluate the accuracy. We can see our VIB net produces lowest RW and Rn, which means we compress. The compression performance is much better than the previous methods, and the error is comparable to the previous methods. And here is the pruned model structure. So we can see because the MNIST actually has a lot of pixels of the MNIST are actually useless. So we also add an information bottleneck in the input layer. So we can see there are only actually 97 pixels actually useful. And we also plot the compression ratio and the mutual information with the first hidden layer and the input layer. So in this figure. So we can see for a regular net, which is shown in the red line, there's no compression, and the mutual information between the first hidden layer and the input layer is always increasing. And however, for a VIB net, in the first stage, the mutual information is increasing, and there's no compression. But when it starts to compress the network, the mutual information starts to decrease and to a relatively low value. We then evaluate the VIB nets on the real-world data set, CIVA10, with a modified VGG16 network structure. And to fairly compare with previous works, which use different modifications of VGG16 and training schemes, we use exactly the same exactly the same setting as them. And in this table, there are 3 different blocks, which means they use different modifications or training schemes. And we run exactly the same scheme and compare with the previous methods. And we can see, and in this setting, we also compare the flop, which is the float point operators. And we can see our compression performance is always the best. And the error is roughly the same as the previous methods. And the error in the processes are the error rate that after fine-tuning the pruned network, and the accuracy is always the best after fine-tuning. And we also run VGG16 on C5100. Also, there are 2 different modifications and training schemes, and we compare with them fairly, and we can also see that our compression performance is better than theirs, and the accuracy is comparable. So to conclude, we proposed a network compression model inspired by the information bottleneck principle, and theoretical analysis shows that the objective tends to accumulate useful information in a sparse set of neurons. And the adaptive sparsity penalty that emerges from our model has advantages over traditional fixed sparsity penalties. And empirical results show that our model can produce better performance than previous compression models. And our code is available online. You can scan the QR code or access it via this link, and discussions are welcomed and in the poster session. Thanks.
All right, do we have any questions? So I was wondering, this is the sparsity is is applied from the beginning. Is that correct? Or
yeah.
Okay. So in contrast to the other approaches, for the most part, do pruning or compression after training. This is doing it.
Yeah.
During
So
training.
our model can add the sparsity from the beginning, but in the experiment part, because some of the models they use fine tuning, and some of the models use the regularization in the beginning. So to fairly compare with them. If they use the regularization from the beginning, we also use it from the beginning. And if they're not, we also fine-tune the chain network.
I have a quick question. Sure. In your information bottleneck objective, you subbed in the Gaussian distribution.
Yeah.
I'm just wondering if there are any like implications for the theory. If you were to use a different distribution there, or why it's a fair assumption that you'd use the Gaussian distribution. So is it a fair?
You are talking about the approximate prior or the
I think both of them were Gaussians, right? Or
yeah, our approximate prior is Gaussian, and the PHI given HI-1 is also Gaussian distribution. So I'm wondering if you are talking about the prior or the...
Or just in general, both?
In general, yeah. I think we have talked about if the prior should be a Gaussian distribution because we want to produce some sparsity results, but there may be other prior that may be better or that can better promote the sparsity. And for the PHI given HI-1, it can be other kind of distributions. Yeah.
Okay. Thanks for the nice work.
Okay.
All right, let's thank the speaker again. Great. The next speaker is Lorenz Mueller, who's going to talk about kernelized synaptic weight matrices.
Sorry about that. So, hi, I'm Lorenz. I'm presenting some work that I did together with Julia Martel and Giacomo Indiveri on kernelized synaptic weight matrices. And maybe just as a little opening remark, I think some of the keywords we heard this morning in the keynote talk by Max Welling are kind of good to keep in the back of your mind as you listen to this talk. While I don't explicitly talk about compression and pruning and things like that, or intelligence per kilowatt hour, this certainly is in the background of what we're doing here. Okay, kernelized synaptic weight matrices, what's that? The idea is let's use kernel functions to reparameterize weight matrices in neural networks. Concretely, like this. So on the left-hand side, you see a weight matrix or an entry thereof. Wij will be rewritten in terms of some new parameters, alpha I, a vector ui, and a vector vj. And those two vectors are fed into a kernel function k. On the right-hand side, you see a little illustration of this. So if you want to know the weight that connects two neurons, like an input on the left and an output on top, you look up the corresponding entry in your matrix, right, usually. Here, what you do is you go to the left and find your little vector ui that has length d, and your little vector vj that has also length d, and you feed them into the kernel, you scale by alpha I, and you get your weight. Why would you want to do this? In our paper, we argue that this can help you in several different ways, in different contexts. It can increase interpretability of your network. It may allow you to impose some structure and some prior knowledge into your network, and it can regularize your network as well. Now, let's get some intuition of what this reparameterization does, some visualization. We can visualize layers in this setting as kernel-smooth functions sampled at a few points. So here we have the pre-nonlinearity activation of a neuron, yj, and then this is just a weighted sum of the inputs xi, right? And the weights now, instead of wij, we have the kernel and this alpha. Now, if we choose a particular kernel and some low-dimensional space so we can plot it, let's take a Gaussian radial basis function and a two-dimensional space, then we can say what the layer does is we place bumps of height alpha I times xi at locations ui. So the ui are like locations where the input neurons inject some bump. And then we sample the sum of these bumps at locations vj. So what we parameterize is where we inject a bump, how we scale that bump, and where we read it out. And then we obtain yj. A different way of looking at the same thing is that we can show that our reparameterization is equivalent to adding a linear layer of dimension d star, where d star is the dimensionality of the space induced by the kernel function. And on the bottom, just as a reminder, what it means for a kernel function to induce a space, you can write any kernel function acting on two vectors as an inner product in some space, and phi would, in this case here, be the function that maps you from the original space of dimensionality d that u and v live in to this induced space. And then you can write out your inner product as in the Hermitian matrix form, and u star and v star would now be the vectors in the induced space. So they have dimensionality D star now instead of dimensionality D. Now let's quickly go through this idea. So on the top, you just see the definition I gave before. Yj equals a weighted sum of xi. On the right-hand side, you have an illustration of what I'm talking about in terms of formulas on the left. We insert what we have on the bottom on the second line. So we insert this Hermitian matrix form of the inner product that the kernel stands for. Then we explicit the sum that's in this vector matrix product. So these are the indices h and k. Now notice that these h and k run over the dimensions of these vectors in the induced space, of the embedded vectors. So they run over dimensionality d star. Then we rearrange terms and we pull the sum over I inside. And what do we get in the little pink box? Well, you get something that looks exactly like a linear layer of a neural network connected with weight matrix U star ki. Of course, U star ki doesn't have the full degree of freedom of the size of your input times d star, but it's somehow constrained by what kernel you chose. Okay. Now, let's go to some results about what you can do with this. And there are several things that I'm just hopping over. Maybe one thing that I'm skipping about induced space dimensionality, I would like to mention anyway. In the context of compression, if you choose very small vectors, so very short u and v, it's very helpful to use a kernel that's more powerful than just a dot product like people often do. So you will improve your performance if you use, for instance, a radial basis function, at least in the situations that we tried. What I will focus on here now is one application to low-dimensional data embedding, and a second one where we regularize a network very effectively with this approach. So first, under the heading of interpretability, some data visualization. We take a pre-trained ResNet on CFAR10, and we just cut off the very last layer, just the output, and add a little bit of a few layers on top, one fully connected layer, then one 2D radial basis function kernel layer with some sparsifying activation function, and the output. And then what you see on the bottom is for each input sample, I plotted where the center of mass of this bumpy landscape that I was showing you before lay. So I can associate now a 2D location with each input sample. And you can really visualize nicely here how the network pulls apart the different inputs that you give it, and it gives you some information about which samples maybe were confused. By the way, this is the test set. This is not the training set, as a side remark. Then you can do the same things at different points. Well, sorry, that was the wrong direction. At different points in the network, and you see that you get some visual idea of how the features that go deeper into the network pull apart the data better. Okay. Now, a more quantitative application we found in matrix completion task, movie lens. So the idea here is you get a big matrix of users and movies. Each user has only seen a few movies, or only rated a few at least, and you try to predict how well they will like some other movies that they haven't rated. Of course, in practice, you'll have to do cross-validation and just hold out some data and then see how well you do on the held-out data. We use an item-based autoencoder called iautorec in the literature, and we reparameterize in this, so it's just like a 1 or 2 hidden layer autoencoder that takes rows or columns of this big user movie matrix as inputs. And in this autoencoder, we reparameterize the weight matrix using these kernel functions. Well, that didn't work too well. It seems to underfit the data. So we came up with a variant where we take the full weight matrix, so alpha ij, now we have 2 indices, so there's a full weight matrix, then entry-wise product with a kernelized weight matrix. And we choose the kernelized weight matrix such, or we choose the kernel such that it has a finite support, and you have a little cartoon of that on the side, right? You have some vectors, locations in 2D again. The black dots might be the outputs, the red dots might be the inputs, and clearly, if the blue circles indicate the size of the radial basis function support, you cannot possibly connect all to all here. You have to set a lot of weights to exactly 0 if you set up something like this. And by doing that, we really managed to improve quite substantially on the root mean square error of the generalization on this autoencoder architecture, and also performed somewhat better than other approaches we found. On movie lens 1M, I should say. Okay, these again are some of the things I mentioned: regularization, interpretable activations, the role of the dimensionality of the induced space. We can maybe get some interpretable latent spaces and impose some structural knowledge that I didn't explain so much. So visit us at the poster, 218. Thanks again to my collaborators, and thank you for listening.
One question, but it needs to be quick.
Okay. Hi, great talk. I was just wondering, does this affect the optimization process in any way? Like, you're basically like using softmaxes and stuff like that inside the network, and I was wondering if that harmed optimization performance, or if there's anything you use to work around that.
So we didn't do anything, but it might be warranted in some cases, yeah. It can be a problem, especially if it's low dimensional, you can build walls, basically. Thanks.
All right, let's thank the speaker again. The next talk is on deep models of interactions across sets, and it will be presented by Devin Graham.
Thank you. So this is a joint work conducted with Jason Hartford, Kevin Leighton Brown, and Siamak Ravenbaksh. So suppose you operate an online movie streaming site, such as Netflix or Hulu, and you want to make recommendations to some user. So your suggestions for new movies should be based on this user's previous ratings, and also on any previous ratings these movies have received. And you may also want to incorporate information from all the other ratings to capture, say, that Netflix users tend to give higher ratings than Hulu users. And if you want to do this for all of your users, then this is the problem of matrix completion. Now, this matrix is what's called exchangeable, meaning that permuting its rows or columns does not change the values of the ratings that it represents. And in this work, we describe how to build deep models that operate on exchangeable matrices and tensors. So in general, there's no guarantee that a deep model will treat two permuted versions of the input data as the same observation. And it may produce very different results. So what we would like to do is to constrain our models to have a property known as equivariance. And that is that they should make the same predictions regardless of which permuted version of the input they are presented with. And so enforcing this requirement amounts to augmenting our data with all possible row and column permutations. And so this is a very powerful idea. And so what we do is describe a parameter tying scheme and prove that it achieves the goal of equivariance. And what's more, we prove that this is the maximally expressive parameter tying scheme, in the sense that violating it results in non-equivariant models. So suppose we're given this input matrix. A standard neural network operates on a vector of observations. So we're going to stack the columns of this matrix to form a vector. This vector will serve as the input to our layer. So we'll multiply it by a weight matrix and produce the completed output. Now let's consider predicting a particular missing entry. This entry is produced as the dot product of the input vector and of this row of our weight matrix. So we would expect that any other movies this user has rated will influence our prediction. But exchangeability means that we can treat all of these elements the same, because any permutation of the columns of our input would change these values' relative positioning in this vector. And so one way to ensure exchangeability is to tie the corresponding parameter values together. Okay, and so that's represented here in red. But similarly, other users' ratings of this movie will influence our prediction. And so once again, we can tie the corresponding parameter values together. And additionally, we are going to allow for influence from all the other ratings, but by the same argument, we're going to want to tie these parameter values together as well. Finally, we'll allow for an influence from the corresponding input value, which here in the input layer will be 0, but again, we're building deep models, and in subsequent layers, that wouldn't be the case. So now, let's suppose instead that the first two columns of our input had been swapped. So we expect that the output matrix will experience the same permutation. And now this output value is the result of the dot product of the shuffled input and this row of our matrix. So if we have the same parameter values in this row as before, shuffled accordingly, then we'll produce the same result, okay? And we'll want to do this for all permutations of the columns. And so we get this weight matrix, okay? So hopefully it's clear from that that this parameter tying scheme will produce an equivariant model. But what may not be clear, and what we actually prove in our paper, is that the converse is also true. So any equivariant model must, in fact, have this parameter tying scheme. So for any model that relaxes this scheme, there will be some ratings matrix for which this model produces different predictions when given a permuted version. Okay, so now to build deep models, we first note that this tying scheme is actually equivalent to using pooling operations over the rows and columns of our input. And so our layer will consist of 4 terms. One that's pooling over the rows, one pooling over the columns, one pooling over both, and one for the original unpooled input. And we'll have a unique parameter for each of these terms. And using this form, we can easily build up deep models. So the first such model we built is the so-called self-supervised. Here we simply hide some proportion of the input values, feed the resulting matrix through a number of exchangeable layers, and try to predict the held-out values. Okay, so the second model is a factorized autoencoder style, where here we pass the input through some exchangeable layers to produce row and column latent feature representations, shown here in the middle. These are then fed through some more exchangeable layers to try to reproduce the now completed input matrix. So this is analogous to classical matrix factorization, but with the key benefit of not having to be retrained to produce representations for new users and new movies. And so in some applications, these user and movie features may be of interest in their own right. So each layer of our model has just 4 distinct parameter values. But in order to achieve higher expressivity in our models, we can simply extend this to multiple feature channels. Okay? And essentially, we just have multiple copies of this weight matrix with unique parameter values in each. And so in this way, we can achieve more expressive models while still maintaining a constant number of parameters. So here we show our performance on the Movie Lens 100K dataset, along with some other recent results, just for comparison. And the dashed line there shows the baseline of simply predicting mean. Okay, and so our model is able to match the existing state-of-the-art results on this dataset. We experimented on a couple others, Flixtor and Duban, and got similarly close to or state-of-the-art results. However, one of the things we're most excited about is our model's ability to handle new data after being trained. So to test this ability, we took a model that was trained on Movie Lens 100K and evaluated its performance on subsets of Movie Lens 1 million. And so for each subset, we vary the number of ratings that we considered observed from 5 to 90% and evaluated the factorized model's predictions on the remaining ratings. We compare against K-nearest neighbors as the only other approach that's kind of capable of incorporating new users and movies without any retraining. And we can see that these methods perform quite well with enough observed data, but our method is beating all of them in all the cases. So in particular, it does quite well with enough observed data and degrades gracefully to the case of just predicting the mean when there's little observed data. And so this led us to further test our model's ability to generalize. So coming back to these data sets, we again took a model trained on movie lens 100K and applied it to Flixtor and Duban. And surprisingly, our results in both cases are still quite close to state of the art, using a model that was trained on a completely different data set. And this inductive application is one of our model's greatest strengths. So this work gives an alternative perspective on a number of recent works that apply to exchangeable data. So if our matrix has just a single row, that is, we have an exchangeable array or a set, and our approach in that case reduces to the deep sets model. Alternately, adjacency matrices and Laplacians are what's called jointly exchangeable, which means that any permutation applied to their rows must be applied to their columns and vice versa. So in our context, this implies that the row and column parameters, the red and yellow ones here, need to be tied together, okay? So if we take this and just use the yellow parameters, then this gives us the basic graph convolution architecture. Okay, and including other parameters gives variations on this. So in particular, adding the green parameter is equivalent to the so-called skip connections of GraphSage. Using only the purple parameter is equivalent to the so-called relation networks. And as you see, there are many, many more. Okay, so finally, just as the parameter matrix for exchangeable vectors can be seen as a building block inside the one for exchangeable matrices, we can extend our layer to higher dimensions simply by repeating the structure for lower dimensions, as shown here. And we prove all of our results for this higher dimensional case as well. So to conclude, we've presented the most expressive model possible for acting on exchangeable matrices and tensors. We're able to achieve competitive or state-of-the-art results on a number of benchmark tasks using models that don't grow with the size of the data. And we also achieve surprisingly good results applying already trained models to completely new data. And finally, we showed that this method generalizes a number of existing methods and can itself be extended to higher dimensions. Thank you.
Great. Is there any question? So I was wondering if this looks a really nice approach. I'm wondering if you're planning on trying it out in other domains, such as there's...
Other than movie ratings?
Yeah.
Yeah, for sure. So we have, so there's another data set we were trying that's music ratings. But there are, in general, this doesn't need to be even just a matrix completion task. Any data that is exchangeable, where you can swap the rows and it's not changing the underlying representation.
There's a lot of biological data, for instance, that this is appropriate for, where graph nets and such.
Sure, yeah, absolutely.
All right, thanks. Time for lunch, everybody. Let's thank our speaker once again.